All right. Hey everyone. Today we're going to be talking and discussing about vector fields as well as gravitational fields. All right, let me fix this. Push it up a little. All right. So, Unit 4 doesn't cover a huge chunk of points on the exam, but AP Physics does tend to backboard a lot of questions off of other units in order to test mastery. So, nevertheless, this is an important topic to cover. All right. So, Unit 4 is discussing circular motion or things that move in circles. Right? There's a couple different examples of things that move in circles that we're going to cover. So the easiest one for me to demonstrate would be something that is tied to a string. Let's see, if you have a human being right here, and then they're holding a string, right? And that string is taut. If you've ever done this before, you hold a string and then you have a little weight on it, and you spin it, it will move in a circle. That's one example of moving in a circle. Another one that they like to throw at you is turns. So if you have a car, let's see if I can draw a racetrack, half a fourth of a racetrack. Let's say you have a car, all right? The car making a turn, this is also circular motion, all right? And the popular example that they like is gravity and planets, as well as electricity. So when you have the Earth, let's say this is the Earth, I don't know. Okay, if you have the Earth and then you move in a circle, right? Let's say we have a satellite right here, right? We have a satellite, then we can effectively move in a circle by orbiting the Earth, right? And that orbit is a circular motion caused by gravity. So we have the force of gravity acting down upon it, mg, right? And we will here learn in a bit, or later on, that the acceleration of anything moving in a circle is going to be towards the center of the circle, right? So before we go into all that schnaz about circular motion and angular velocity, we should talk about two different things: gravity and vector fields. What is a vector field? Well, we know that vectors are things with magnitude and direction, right? Typically, you express a vector with an arrow, right? If it's an acceleration vector, then it is saying that there is an acceleration towards the right direction, right? If we have a velocity vector, it tells you something is moving towards the right. A vector field is something, if you want to learn a lot about it, you go into differential equations. But a vector field is basically something, let me draw a coordinate grid. A vector field is a lot of vectors lined up that tell you the direction that something will go, right? So for example, this vector field this is a vector field that means that any object or particle inside of the field will be going up and to the right, right? This vector field says that all particles in the field move to the northeast, right? Well, that's pretty simple, right? Well, where can it get more complicated? A vector field can also have curved vector lines, like so. As you can see here, not all the vectors are pointing in the same direction. Now they're moving in a circle, right? And this vector field is saying that any particle that exists in the vector field will move in a circular pattern, right? Now, why is this applicable to gravity? Well, let's say we have the surface of planet Earth. This is Earth. That's the surface. All right. Now there is a permanent vector field, right? Let's say you're in your room watching this right now, right? You're on a chair, right? I'll draw your chair. Hopefully you're in a chair. I don't know. Hopefully you're comfortable. All right. That's my best rendition of a rolling chair. All right. So you are sitting in this chair, I don't know, tablet, computer, something, watching a lecture. Well, anytime you're on planet Earth, there is a vector field that points down. All right. This vector field is an accelerational vector field. And you might be able to guess what this acceleration is. The acceleration due to the vector field is equal to g, the force of gravity. And it is saying that in Earth's vector field, all particles with mass experience an acceleration of g down toward the center of the Earth. The Earth's vector field is a gravitational phenomenon that affects all objects with mass. That's pretty key, because the condition for being affected by the vector field is your mass. There are other examples, such as electrical fields, right? So let's say we have an electrical field. Now this is, let me start off with some prerequisite knowledge that not everyone might know. So in physics, chemistry, the universe, everything that applies to the world, there are three fundamental particles. Three fundamental subatomic particles. They're called neutrons, protons, and electrons. Neutrons have zero charge. They have no net charge. Protons are positively charged, whereas electrons are negatively charged, right? We know a couple things about these, simply, that like charges repel, as well as opposite charges attract. Okay. So now I will give you two different instances where the vector field can differ from your normal conceptual logic. First is the electrical method. So let's say we have a capacitor. It's okay if you don't know what a capacitor is just yet. And each capacitor has a positive and a negative side. So this is the positive, and this is the negative. All right. Electricity always flows from positive to negative. Sorry, that's my bad, actually. Electricity flows from negative to positive, and that is a rule of diffusion. So the vector field here, right, in green, this vector field is an acceleration. It's an acceleration for a negative charge, right? So if you were to put a neutron here, this white thing is a neutron, the acceleration would be 0. That makes sense. They're not charged. If you put a proton, no, wait, let's start with electron. If you put an electron here, the acceleration is positive. It goes to the right, right? We're going to assume that to the right is positive. Acceleration is positive here. Well, that makes sense because the condition of the vector field is that anything with a positive charge will go to the right because the arrows are pointing to the right. Now let's put a proton here. If we put a proton in this vector field, then the acceleration will be negative, right? Now think about why that is. That's because the vector field is telling you that everything in the vector field with a negative charge goes to the right. So logically speaking, the proton, which has a positive charge, should be going opposite the direction of the vector field. Electricity is a wonderful example because you can see that something with the reverse condition of the vector field goes in the opposite direction. Now, why don't I go back to gravity and explain why electricity is so fun? Let's say we have planet Earth, right? And this is a huge rendition of planet Earth. And the force of gravity acts down, right? But it doesn't just act down. When you zoom out far enough, you see that the force of gravity is actually acting towards the center, perpendicular to the surface, like so. All right? So when you have, let's say, anything with mass, let's actually put it up in the sky, like an asteroid, anything with mass. This is an asteroid, right? It has mass. It has mass, right? The asteroid experiences a force that goes downwards. Acceleration is experienced downward. This is different from everything we've experienced so far in dynamics because dynamics was all about contact forces, things that had to be touching. Well, in this unit with vector fields, nothing technically has to touch. Rather, the gravitational phenomenon of the world causes the masses, it causes anything that has mass to be attracted to another thing with mass. AP loves planets because planets are so massive, they create their own gravity. They create a noticeable gravitational field, right? So conversely, if you had, let's say, a photon, if you don't know what a photon is, it is a packet of light, just light, and it has no mass, right? A photon that is shooting across the Earth's atmosphere will not have any amount of gravity acting upon it. A equals 0. This is because a photon has no mass. The conditions for having a gravitational acceleration is to have mass. Since a photon has no mass, we can't say that it experiences gravitational acceleration. There is not a single thing that I know of that we can clearly visualize that has negative mass. Technically, if you have a particle of antimatter, right? If you have, that is invisible. If you have something like antimatter, in theory, since its mass is negative, the acceleration experienced by antimatter should be opposite of the gravitational field. Acceleration will go up. That's hard to visualize. It's easier to visualize the electrical one because you can have positive and negative and neutral charge. Now, how do these relate in equation form? Well, these two are both fields, and it turns out Field's equations are nearly identical. The equation for gravitational acceleration, right, is G equals, that's a little g, I want to do this in a brighter color. Little g equals big capital G times m1, m2 divided by r squared. Right. Now you're probably asking me, Mr. Cho, what is big G? So big G is the universal gravitational constant. And it is expressed as, so here, G equals m cubed, wait, that's my bad, that's the unit, 6.67 times 10 to the negative 11th m cubed divided by kilograms second squared. There's no real neat one we can do like newtons here. That's just the unit it is. And that's a really odd number. Well, think about it this way. The Earth's mass is so massive. Well, that's kind of odd to say. The Earth's mass is so large that the gravitational acceleration equals 10 meters per second squared, regardless of whatever is attracting on the surface. Now, because the Earth's mass is so enormous, it overcomes the capital G constant and makes it a whole number. 10 to the negative 11th is actually nothing to joke around with. It's very, very small. However, the mass of the Earth is so large that it can make it a sizably large number, like 10 meters per second squared. All right, let's break this down. So G is the gravitational constant of the universe. Gravitational constant of the universe. All right. Now, what is m1? This is the mass of object 1. What is m2? This is the mass of object 2. And r squared is, well, r is the distance from the centers of each object. All right, now that is the simple way to put it, but you may have noticed that G depends on both M1 and M2. Right. Well, we say G is 10 meters per second squared, right? Because the Earth's gravitational pull is 10 meters per second squared for practically anything that we can work with, right? So let's compare the mass of you. Well, Mr. Cho weighs around, nowadays, I'd say 70 kilograms approximately, right? And we're multiplying by 70 kilograms. That's a cool number and all. But what is the mass of the Earth? The mass of the Earth is 5.972 times 10 to the 24th kilograms, which your mass, no matter how large, fat, or obese you think you are, you guys aren't. Trust me, the Earth is fat. The Earth is huge, all right? 5.972 times 10 to the 24th kilograms, enormous. And even then, the Earth isn't even that fat of a planet. We have Jupiter, for all we care. All right. So because the mass of the Earth is so enormously larger than your mass, in the equation, when we're finding the gravitational acceleration of a planet, your mass is negligible. You don't matter in the equation. Neither does a satellite, which could weigh 10 tons. That still pales in comparison to the Earth's mass. So that's why we really don't care about how much mass the other thing has. What's important is, let me rewrite the equation down here. What's more important is if we have G equals capital G M1 M2 equals R squared. Let's say M1 equals the mass of the Earth, right? What if M2 equals the mass of the moon, right? We have the moon orbiting us. Is the acceleration on the moon that much different from 10? Well, the moon is way more massive, right? What's the mass of the moon? The mass of the moon is, Lord, 0.07346 times 10 to the 24th kilograms. Now, why did I write a scientific notation in an illegal way? It's because, look, these 10 to the 24th, I wanted to keep them 10 to the 24th. That's why it was written that way. You could approximately say the moon's mass is equal to 1.2% of the Earth's mass. And I know that's ridiculous too. Now, 1.2% is fairly small, but it's also not negligible. It's not completely negligible. Now, why doesn't the moon just crash into the face of the planet? Well, it's because of two different things: the radius as well as the angular velocity. Now, we'll explore angular velocity in a different lesson, but the radius here matters. The radius says that as two things grow larger and apart, the gravitational force decreases exponentially. Right? So, when you have two things, let's say we have a planet here, and planet number 2, and M2, they exert a gravitational force. They pull each other together. So M2 will come towards and M1 will come towards. Rather, since M1 is larger, it's just going to be M1 pulling M2 towards it. But there's a small force of M2 pulling it back. All right, if we have this, let's say this force was force of gravity called Fg. Oh, Lord, Fg. I know we say Fg is like the force of gravity on Earth, but this is also a force of gravity. If we had them at a distance of r, right, then Fg would equal capital G m1 m2 divided by r squared. That much is simple since we're working with easier numbers, or variables, or units rather. All of the above, basically. If we had m1 here and m2 at twice the distance, 2r, then the new Fg would be equal to G m1 m2 divided by 2r squared. See that? Which means it's G m1 m2 divided by 4r squared, right? And that's our force of gravity nu, or force of gravity 2. Now, the new gravitational force between these. And we know that the force of gravity 2 is, look at it, the only difference between the force of gravity's equation, and the force of gravity 2's equation is this 4. So that means that the force of gravity 2 equals 1/4 of force of gravity. So that's what I mean by a squared relationship. If you double the distance between them, you have to divide the original force by 4. Thought experiment: if you tripled the distance between them, then you would divide it by what? 9, because that's 3 squared. All right? So, as a quick ending note, the equation for electrical forces, repulsion and attraction, I couldn't find the word, is actually identical. The force of electrical repulsion or attraction equals, I think the big constant's called capital K, Q1, Q2 divided by r squared. It kind of looks identical with different numbers. Q1 is the charge. Q2 is also charge of particle 1. Q2 is the charge on particle 2. R is still the radius or the distance between centers, right? And K is a constant, right? We call them constants because they don't change. So, knowing all this information, right, we have the ability to calculate electrical charges, the force on electrical charges, attraction and repulsion, as well as the force on gravitational phenomenon for anything with mass. So, K, if you want different things for it, so K can possibly equal, you don't have to write these down because they'll be given to you, 8.988 times 10 to the 9th Newton meters squared divided by Coulomb squared. Okay. I believe that's so. Maybe I am incorrect. 8.988 times 10 to the 9th Newton meters squared over. Okay, let me rewrite this. It's actually, the units are the only thing wrong. Newton, kilogram meters cubed divided by second squared Coulomb squared. A Coulomb is a unit of electrical charge, right? So that's that. If you guys would like to memorize that, it's all for you. I don't recommend it, all right? And so if we had two particles, one with positive charge and one with negative charge, this equation tells us that the greater the charge of each individual one of these, the greater the force of attraction. Also, that the greater the distance between them, the lower the force of attraction exponentially, right? So that is the introduction to Unit 3. All right, I hope you guys find this lecture useful, even though it's in a remote format. All right, have a wonderful day. I will see you tomorrow.